Welcome. My name is Randy Ellis. In this session, we'll review some prerequisite material for our course on nonlinear data analysis, and this prerequisite material is more linear algebra. Here, it's on projection and regression. The main concepts for this session are we'll look at the column space of a matrix, and we'll look at orthogonal projection. Originally, we'll just look at it we could think of it in 1D. We'll look at it in 2D and see how that extends to higher dimensions. We'll look at the normal equation for this projection problem, and then we'll observe that regression, when we have independent and dependent data, is in fact a projection problem. So let's begin with a 1D projection. Suppose we're given a basis vector and another vector, and what we want to know is what multiple of the basis vector is nearest to the given vector, and the multiple is some scalar weight which we'll call W. So the nearest vector is that particular vector that we'll call P as the projection, and we'll define that as a weighted or a scalar multiple of the basis vector. And we can define the error vector as the difference between our given vector C and our projection vector P, and we'll call that E. So E for error. And the goal is we want to minimize that error of projection. To do that, what we can do now is let's think about a subspace. Suppose we have two vectors, A1 and A2, that are linearly independent. So for two vectors, that just means neither is zero and they're not scalar multiples of each other. So they are the basis for a two-dimensional vector space. Now the question that we want to answer is, suppose we're given a new vector C. We want to find the projection vector that's in that vector space spanned by these two basis vectors and is closest to C. So now let's set this problem up. The vector P, the projection vector, has to be a linear combination of A1 and A2. That's because the projection vector has to be in the vector space that the basis vectors span. So let's define P as being the weighted sum. So we can look at this as it's the weighted sum, W1 times A1 plus W times A2, or we can collect these terms into matrices and vectors, and we can say that this is the matrix A1, A2 times the vector W1, W2, and we can write that as a matrix A times a vector W. Let's observe that we are given these values in A, and we're given the values in C, and we want to find these weights W that cause this projection. So we'll use the same method as before. We'll define an error vector, which is the difference between our given vector and our projection vector. Now, let's take a look at this geometrically. The error vector has to be orthogonal to every vector that's in the space, in the vector space that's spanned by A1 and A2, which are acting as basis vectors. We can say then, for sure, it has to be orthogonal to A1 and to A2. If it's orthogonal to everything, it's orthogonal to anything. And now we can imagine this. Suppose we have our vectors A1 and A2, and now we're given a new vector C. What we want to do is we want to find this projection vector P that lies in the subspace spanned by A1 and A2. And this error vector is going to be the difference between C and P, and it's going to be orthogonal to P, to A1, and to A2. Let's look at the algebra. So if it's orthogonal, that means that if we gather these, that the dot product of A1 and E has to be 0, the dot product of A2 and E has to be 0. One way of writing a dot product is by transposing the left vector. So we can say A1 transpose E, A2 transpose E, each have to be 0. We gather them together and we have a matrix. But that matrix is the same as saying A transpose times the error vector has to equal 0. When we go through the linear algebra that we cover in the prerequisite material, what that means is that we get this, which is this is called the normal equation for the data in the matrix A and the data in the vector C. So if we take A transpose A, multiply it by the weight vector, that's the same as A transpose times C. And that's a linear equation that we can solve. And if these vectors in A are linearly independent, that is, if they form a basis, then A transpose A will turn out to be invertible, and so there's a direct, mathematically, there's a direct analytic solution to this. And this extends, it doesn't matter how many entries each vector in A has, or how many of them are, as long as they're linearly independent. So what this does is, this is a way to project a new vector C to the column space of A. Let's switch gears briefly and now think about statistical regression. So if we have a set of observations, these ones are the independent ones, and this is the dependent. We say that independent means usually they're experimentally controllable or they're gathered in some way. And we have some mental model or mathematical model that this entry C is somehow dependent on the independent one. Typically these are controllable, these are observed, but that's not necessarily true depending on what the experimental setup is. So regression is relating the independent and the dependent values by some underlying function. We could say that what we need to do is learn. So if this is a general function, what we want to do is we want to learn the entries of this argument which we're gathering into a vector. So our actual value is C, and our model is we'll compute F of given the data values and our weights. So residual error, there are many kinds of error, and what we'll usually talk about is residual error. This is the actual value minus the model value. So what we're saying is that the residual error, so now the residual error depends on the arguments that we're learning. We'll define that as the difference between the dependent value and the model value that we have computed. So we can gather these into a vector. And so we can say that there's not just an error term, there's an error vector. What we want to do, of course, is we want to minimize the error between the model and our data. In doing this, the common way that we'll do it is with linear regression. So what that means is we have a linear model. So what we're saying is that each time we gather all of these entries together, and we're saying that the model, the mathematical model of the data is that they are linearly weighted. And what we want to do is minimize the error between the data and the model. And this, when we formulate it, says that the ith error, given the weights, is defined as the ith dependent value minus a weighted sum of the independent values. And we gather all of these together, and what we have, so what we've done is we've stated this statistically, and then we've used a linear model. What we get is actually the same equation that we had when we were doing projection. So that means that if we're trying to minimize squared error, it's the same as performing orthogonal projection of a dependent vector to the vector space of independent data. That means we can use the normal equation to solve this problem of linear regression. So, how can we summarize this material? Suppose that we have some independent data that are presented in a matrix. We have dependent data that are in a vector, and the number of rows of the matrix and the number of entries of the dependent vector are the same. The column space of the matrix is some vector space V. We have a projection vector that's inside that. We have weights, and what we want is we want to find that projection vector that is a weighted sum of the data. We form the error vector. The orthogonal projection gives us the normal equation. Linear regression is we want the A times W to be approximately C, And this is the same solution as orthogonal projection, and we can get a single simple equation that expresses the weights in terms of the dependent and the independent data.